Lesson: Fine-tuning and optimizing models for production. Fine-tuning and optimizing models for production is a critical component of deploying AI solutions effectively in real-world applications. This process involves enhancing a pre-trained model to meet specific performance criteria and ensure it operates efficiently within the constraints and demands of a production environment. The journey from training a model to deploying it in production requires a deep understanding of various optimization techniques and tools, each tailored to address specific challenges that may arise. One of the most significant challenges in fine-tuning models for production is ensuring that they generalize well to unseen data while maintaining efficiency. Transfer learning is a valuable approach here, where a model pre-trained on a large dataset is adapted to a new, often smaller, dataset. This technique not only saves time and computational resources, but also leverages the model's existing knowledge to improve performance on the new task. For instance, the BERT model, developed by Google, can be fine-tuned for specific NLP tasks like sentiment analysis or question answering by adjusting its parameters on task-specific datasets. To implement transfer learning effectively, practitioners must identify the layers that require retraining. Often, the latter layers of a neural network are crucial for task-specific features, while the initial layers capture more generic features. By freezing certain layers during the training process, one can focus on adjusting only those parts of the model that contribute directly to the task at hand, thus optimizing computational efficiency and reducing overfitting risks. Hyperparameter tuning is another cornerstone of model optimization. This process involves adjusting the model's hyperparameters, which are not learned during training, but are crucial for dictating the learning process. Techniques such as grid search and random search have traditionally been used, but they are computationally expensive. Bayesian optimization offers a more efficient alternative by building a probabilistic model of the objective function and using it to select the most promising hyperparameters to evaluate. This approach not only accelerates the tuning process, but also often finds better solutions than exhaustive searches. Practical tools like Optuna and HyperOpt provide robust frameworks for hyperparameter tuning. Optuna, in particular, allows for flexible and efficient exploration of hyperparameter spaces through its define-by-run interface, which dynamically constructs the search space during execution. This flexibility is crucial in complex models where the search space is not easily predefined. Once the model's performance is optimized, attention must turn to deploying it in a production environment. Here, model compression techniques such as quantization and pruning become essential. Quantization reduces the precision of the model's weights, thereby decreasing its size and computational requirements without significantly impacting accuracy. Pruning, on the other hand, involves removing redundant neurons or entire layers from the model. These techniques are particularly important in resource-constrained environments, such as mobile applications or edge devices. TensorFlow Lite and ONX are two frameworks that facilitate model deployment in production settings. TensorFlow Lite allows models to run efficiently on mobile and IoT devices by applying optimizations like post-training quantization. ONX, or the Open Neural Network Exchange, enables interoperability across different deep learning frameworks, allowing models to be trained in one framework and deployed in another, optimizing for the best performance across platforms. Real-world case studies illustrate the impact of these techniques. For example, a leading e-commerce company fine-tuned a BERT-based model to enhance its recommendation system, achieving a 15% increase in click-through rates after optimizing the model with quantization and pruning techniques. This not only improved user engagement, but also reduced server load, demonstrating the dual benefits of fine-tuning and optimization. Continuous monitoring and maintenance are vital for models in production. Models can degrade over time as they encounter new data distributions, a phenomenon known as model drift. Implementing a robust monitoring system can help detect such drifts, enabling timely retraining. Tools like MLflow and TensorBoard offer comprehensive solutions for tracking model performance metrics and visualizing training processes. MLflow, for instance, allows for experiment tracking, model packaging, and serving, providing an end-to-end solution for managing the machine learning lifecycle. The ethical considerations of deploying AI models must not be overlooked. Ensuring that models are fair and unbiased is crucial, especially in sensitive applications such as hiring or loan approvals. Techniques such as adversarial testing can uncover biases by simulating potential worst-case scenarios. Furthermore, organizations like IBM have developed open-source toolkits like AI Fairness 360, which provide metrics and algorithms to detect and mitigate bias in AI models. In conclusion, fine-tuning and optimizing models for production involves a multifaceted approach that encompasses transfer learning, hyperparameter tuning, model compression, and ethical considerations. By leveraging practical tools and frameworks, AI specialists can ensure that their models not only perform well on specific tasks, but also integrate seamlessly into production environments, offering scalable, efficient, and fair solutions. As AI continues to evolve, these practices will be crucial in maintaining the relevance and effectiveness of AI systems in diverse applications.